There we go. Great. Okay, so we are going to go, this is going to be a conceptual lecture. It's going to be on model conceptualization. Okay, so I posted the slides for this for those who may be interested in following along. I don't have time to go into all these slides, but I do have time for some of the important ones. Okay, so let me make this full screen here. Okay. So this lecture was originally embedded in a broader discussion of the modeling process, and I wanted to give you an overall sense of modeling, the flow of modeling processes. We're going to focus for this lecture on this first stage of problem conceptualization and qualitative problem mapping. But before we build up the sort of models that we've been using in these processes, or in this boot camp, there's often these two key steps at the beginning, and arguably those are the most important steps of the process. We've been concentrating on model formulation and use of models to gain insight down, say, in these last two categories, and we saw yesterday some model calibration and testing issues. But I wanted to talk about these first two, okay? With the emphasis being that the real outcome from a modeling process that's of greatest value is, in my view, the change in understanding that takes place. Now, what's most key for undertaking this process as a whole is to do so incrementally. And I can't overexpress the importance of building up models by placing new components in them, running them, and learning from them. Even if you feel they're not yet done, the insights you get from adding things into a model over time and running it and observing the results will give you profound value. And often you end up with a model that's as rich as you originally anticipated, but it's richer in much more savvy ways, in ways that actually yield greater value than you originally anticipated. So the idea here is that with incremental model development, you should build a model up in a step-by-step fashion. With each iteration, the model is modified in some small fashion. You're adding some feature into the model. There's a logical chunk of work that's performed. And as a cross-check, since the work of Axelrod and Axtell, and a very nice book on modeling that was published about probably a bit over 10 to 15 years ago, they talk about docking a model against earlier versions. So you add a feature in, maybe you initially disable it, still give comparable results to the old version. In other words, have you broken anything in the model by adding this new feature? And then you turn on the model, and you turn on this new feature, or you otherwise enable it or take advantage of it, and you observe the results. You observe what changes there are in the results. There are times where you'll add a feature in. Let's say you've got a model of spread of innovation, and initially you assume that it's spread via random mixing between people, so any person can spread it to any other, and then you impose a network. One thing you can do to kind of check that is when you impose that network, you can say, okay, we're going to impose a network that everyone's connected with everyone. Does it still spread in the old fashion? And have confidence that you haven't totally changed the dynamics in some unexpected way. So often by adding in a new feature, you can set it so that that new feature doesn't yet have a very different result, and you can make sure that you haven't totally altered model dynamics. Now, a key point is that these incremental versions often produce insight. They help you spot errors, and they can sometimes be demonstrated to model stakeholders. So what are some of the benefits of incremental development? Well, you have greater understanding about where the model patterns come from. You realize that I only saw this really interesting behavior when I added this feature in. If you go and you say, okay, 6 months from now we're going to have a great model, we're built towards that, and that's when you start running it, Maybe that model has lots of features in it, and you see really interesting things, but you don't know where they come from. And it can take a long time to experiment with that big model to figure out which feature is leading to what sort of behavior, which set of features. If you build it up incrementally, you will get that sort of understanding often along the way in an automatic fashion, because you'll add in a feature, you'll see some new behavior, and you'll say, oh, I haven't seen this previously. It's something to do with this feature. So you learn along the way about big aspects of behavior. Yes, Joanna?
So with this incremental model development,
yeah.
Is version control straightforward?
Yes. So this is one of the best practices that I'm hoping to cover this afternoon. But model version control is another best practice from software development that is very highly advised. And so there, the idea is saving away successive versions of your model. Now, the ideal way to do that is with version control software, where like Git or Subversion or in earlier generations RCS or CVS. At the least, you want to save away named versions that, version 1, version 2, version 3. So you can always have recourse to earlier versions, and so they are clearly delineated. And then you want some way of recording when you get model results, which version gave rise to these results. You want metadata maintained so that if you go back and you have to reproduce these runs that you've reported in a paper because the reviewer asks you to make some modification or display some output, you want to have total clarity on what model version was used to produce this, what assumptions and the parameters and what random number seeds were used to produce this, so that you can go back and recreate it easily, right? We have a tool built by one of the students in my lab, Priyesh Gomik, that automatically records that information. So when you run the model, each time you run an experiment, it saves away a version of the model. It actually saves away the values of the parameters, and it saves away the random number seed, and it records the time at which it was run. And that's the sort of thing which can allow for really easy reproducibility from a model, okay? So one benefit of incremental development is a better understanding where model patterns come in. A second benefit is the capacity to diagnose bugs sooner. If you added this thing into the model and you see a problem, you get a null pointer error, or it says index out of range, or the model just doesn't show anything, at least you've only made a few changes between when it was working and now, so you know probably it was one of those changes, very likely, that led to this adverse behavior. If you went 2 months before observing it and only then found an error, there might be hundreds of changes. You're not sure which of them introduced the problem. If you can run it again after just a few changes, you'll be much more confident about where that change came from. Very importantly, ladies and gentlemen, you can change the direction of modeling based on learning that occurs. So ladies and gentlemen, often in this process, we're learning along the way about model patterns, about what the model is producing, what interesting things it's capable of generating. And as a result, there's learning that goes on. There's learning and there's refinement of your thinking. And sometimes you will take the model in its next step to go in a different direction than you would have originally anticipated without that learning along the way. In other words, by observing, oh, you mean just with these couple of features, the model can produce this really interesting pattern. Maybe that will mean you end up deciding to publish an interim paper on just this smaller model. Or maybe you say, well, given what we're seeing out of the model now, maybe we should put aside the plans to do X and Y, and we'll just do Z now, and go right on to Z right now. So in short, you learn along the way by incremental model development, and that permits you the ability to change course to take into account that learning. If you have important stakeholders who are interested in your model, some of these incremental versions you may wish to show to your stakeholders to get feedback from them. I've tried to emphasize here, often you don't fully elicit tacit information from stakeholders by just talking with them about issues. Sometimes the model, by showing them patterns that are output by the model, by showing them the model results, that will sometimes elicit understanding that would otherwise go untapped. And so the fact that you have this model being built up incrementally can be very valuable for eliciting some understanding from people that otherwise might not have been forthcoming from them. There can be greater clarity and prioritization of what to do next. Ladies and gentlemen, we tend to be very poor at estimating how long it takes us to add in certain features to software, and to a model is no exception. And if you can do things in smaller chunks, we can often be more accurate in thinking how long is it going to take us. We tend to be very inaccurate when we imagine big chunks of work, because we're thinking in very imprecise ways. We're thinking in very abstract and very amorphous ways. But if we're thinking about a small chunk of work that might take a few days or a week, maybe two, we're going to be very concrete in thinking how long that's going to take. Even to the point of thinking, well, next week I have to be out of the office for my friend's wedding on Thursday and Friday, and you know, I'm not sure when this data is going to come in that I've been counting on. We tend to think in much more concrete ways, so we tend to be able to estimate better. It's also a matter of morale on the part of stakeholders that as you're building up this model, if you can show progress, it gives them confidence it's going somewhere. Okay, so incremental development is highly valued. Now let's talk some about this issue of model conceptualization and sort of thinking about the scope of the model. This is an area of active work for Jeff and myself, and I'm not going to say that I think we have the silver bullet on this, far from it. But I think we're learning, and that's the important thing. We're moving forward with our learning. There are several frameworks that people have put together to try to characterize models, to try to describe them and think through them at a conceptualization level. The one that I tend to use these days is one called PARTIES. And it's an acronym standing for these elements here. And it's a way of thinking through, you know, in my model, what elements are there? Well, there are properties, there are actions that take place, changes that take place over time. There's rules, so there's certain conditions under which those actions take place. There's some time, and you're going to have to decide, is time continuous or discrete, and what's the length of time? What is sort of the time unit or time horizon over which you'll run this model? There are interventions you're interested in. There's some environment, spatial or topological, you know, in terms of networks, and there's states of agents. Those aren't necessarily in the order I would prefer, but it's a nice acronym to sort of knit them together. Those will get you thinking about some of the pieces. This is very close to Ross Hammond's, and I certainly borrowed from Ross Hammond's way of thinking about it. Ross is an eminent modeler at the Brookings Institution, and he talks about properties, actions, rules, time, and environment. Just to combine states and static things into properties. I would call them kind of parameters versus states. And he tends to put aside interventions as a point of consideration. But in other ways, it's very similar to the framework I use. Another framework that's used to characterize models, to describe them systematically, is this ODD, the Overview Design Concepts and Details Protocol for ABM design that was advanced by Volker Grimm. I believe Steve Railsback may have been part of that initiative as well. And there's a set of ABM modelers, some of them from ecology background, who came together to specify this. Volker Grimm is himself from ecology. And so its primary use is as a specification protocol. And we have published models that have been characterized using ODD systematically as a way of communicating with reviewers. And there's three broad components in light of the three letters of the acronym. The overview, which has to do with the model goals, the high-level scope, and the design, goals being key. The design concepts, different aspects of the design, and remaining elements. And Railsback and Grimm have a decent book, Individual and Agent-Based Modeling, where they go into this in more detail. Okay, so now I'm going to really dive into the model conceptualization components. One of the most important principles for model conceptualization is that models are problem specific. All models are simplifications, and in George Box's terminology, wrong in the sense that they're a simplification of the world. They're wrong in the same sense a map is wrong. It's incomplete description. It's a simplification of the world. It's an abstraction of the world. But some models are useful. And in order to build a useful model, one of the most important things you can do is be clear about what the purpose is for which you're trying to use this model. You don't want to get stuck in the notion that you're going to model a system. Some very promising modeling projects have gone off the rails by an interest saying, we're going to model the immune system. Now, it sounds laudable, but there's no bottom to that. You could just go on and on and on about all sorts of details, and unless you have some sense about which things are actually germane to the questions you're trying to bring to bear, you may end up spending huge amounts of time on very low return investments in terms of building aspects of the model. So you want to have some clarity as to what are you trying to get out of the model. And it may not just be one thing, but it should be a small number of things. To what degree are you trying to explain reference modes? To what degree are you trying to explain the rise of type 2 diabetes in Saskatchewan's Aboriginal population? Or to what degree are we trying to explain the higher prevalence seen in First Nations reserves of STIs? So there may be some reference about some broad patterns that are noted statistically that we're trying to characterize. It may be that we're trying to understand certain policy impacts, that we would like to be able to evaluate the impacts of policies focused on reducing childhood obesity in New South Wales in the scope of 10 years' time. Or maybe we're just trying to sort of to develop confidence that we can rule out a certain common hypothesis for why we might be seeing a certain trend in empirical data by putting the pieces together and asking, is this a big enough effect to generate that trend? We did that with the arrested immunity hypothesis for chlamydia in Canada, for example. So establishing a clear model purpose is very important. And Don Burke and Josh Epstein have listed dozens of purposes of models. There's many good purposes. These are just a few. But you want to have some clarity about what sort of things what would a successful modeling project look like? It may be a model purpose. The model purpose may be a research question, but it needn't always be. In system dynamics modeling, for example, the purpose is often to catalyze change in some group or to help stakeholders from different areas of an organization work together more effectively. It's not always a research question, although sometimes it is. Often it is. Sometimes it's a goal of a more practical sort, or something having to do with the human theater. So being clear about the problem is helpful. And one reflection here is that adding factors into a model does not always improve that model. Sometimes it does enhance the model, but sometimes it draws our attention away from some basics that are really important, and it causes us to spend time in ways that aren't nearly as fruitful. Okay, let's see. One thing I'll say about system dynamics models, Kurt had a comment on this that I thought was one of the more insightful comments I've heard from a modeler. Kurt is someone who, like myself, has practiced several types of modeling, including system dynamics modeling and agent-based modeling. And he was working on a project for a Ministry of Health where he was using system dynamics as the main tool for the modeling for a while. And he was about 3.5 months into an internship of 4 months in length, and was really banging his head against the wall with respect to characterizing certain types of features. And so he asked me, he consulted with me and asked, so he could stick with system dynamics and get some pretty good insights out of it with this aggregate model he has. He just is going to have certain limitations, and he'd have to really try to force fit certain types of needs in order to get certain types of insights out. It would not be an easy or comfortable thing. Or he could try a different modeling approach for a brief period of time. Well, he could try a different modeling approach. And I suggested to him he spend 1 week and he try a modeling approach that would take him out of pure system dynamics approach and use agent-based and discrete event modeling, I think was the idea. Just try for a week's time. He had about a month left. And I said, try for a week's time and then evaluate it. Learn from that and figure out if you want to go that direction. And he commented to me after that week, his comment was, he felt before that week, he had felt like he was walking down a set of corridors, really boxed in, trying to figure his way through a maze of sort of small, tight corridors, always working within these constraints and being driven hither and yon by these corridors, and they're windy.
I use those words. Hither and yon.
Yeah. A maze of small passages all looking alike. And then he said once he tried this other modeling approach, he felt like he left the corridors and ran into a field that was just completely wide open. He just could run across the field in any direction he felt like, and he felt liberated from the strictures of tight modeling constraints. Now there's a danger there. There's a benefit there. He felt he could suddenly characterize these interventions that he had been unable to really adequately characterize previously. But the danger here is that in a system dynamics model, in an agent-based model, we're less constrained than in system dynamics. So we can add in all sorts of details to our model. And where we have to exercise caution is different. In system dynamics aggregate models, there's often a lot of attention about how to force fit it to capture certain types of needs. Force fit is not a kind word for it. And how to kind of characterize it within the constraints of system dynamics often takes a lot of attention. And you can do some fairly elegant things in clever ways, but it takes a lot of kind of thinking about exactly how to do it. In agent-based modeling, it's very easy to throw new things in. You can add the kitchen sink quite easily. And this is one of the dangers that software engineers have when they're first using object-oriented programming. Putting modeling aside, they will often throw things in very readily just because they can. And the danger here is with modeling, sometimes throwing more things in does not help the situation. In fact, it complicates the situation unnecessarily. So we can add deep levels of detail. We can have adaptive behavior changing based on a person's context, sophisticated decision rules, many properties and attributes of a person, but we haven't necessarily increased the insight, and we may be at a loss to try to secure insight from these new features. There's just too much going on. So a few general principles here. So one issue is opportunity cost. We have limited time. And if we put the time into one thing, we're often taking that time away from something else. And it may be taking away from something that's more important. So we have to be very careful about when putting things into the model, because there's unintended consequences there. There's a principle in software development called YAGNI. It's the you ain't gonna need it principle. And the idea here is that in software development, software developers are often feel moved to add things in that aren't fully needed. They're speculative. They're things that might be needed. They could be sought by a stakeholder down the road. And we as software developers have to be quite careful to restrain ourselves to put in unnecessary, to basically over-engineer it. So with the Yagini principle, the idea here for modeling is start simple and add as one develops confidence in and understanding the model. And as one learns from it, as you actually add things in and observe the results, then you can start to think about prioritizing new features to add in. If you think ahead of time, I want to add X, Y, Z, A, B, C, D, E into my model, and you wait to learn until all those things are in there, you've missed a grand opportunity to pare that list down through learning along the way. You may add in only X and Y, and then you discover, well, the next 6 of them are unnecessary. We only need H, and then we're done. So the Yagini principle is very important in restraining yourself, because with the failure mode with agent-based modeling is you put too much in, and then you find yourself mystified. I've met students whose PhD thesis ended up like this. They added in a huge amount of stuff, and they waited till it was all in there to run the model, and then it showed interesting things, but they didn't know where to start to analyze it. It's interesting. Yeah, well, okay, what does it tell us? Well, it tells us if all these things are in there interacting in these complex ways, we see these patterns. But how does that help us? And I know one student, brilliant student, she ended up throwing that all away and building a small system dynamics model just so that she could kind of think through things at a more basic level. So that's the big risk with agent-based modeling. You throw too much in, and you don't learn along the way. If you learn along the way, at least you end up with a much more savvy model. And maybe every bit as rich as the original model you had planned, as the model you would have built if you had anticipated everything, but it's much, much, much more educated. It's based on priorities that have been informed by learning along the way. Okay, so what are some key steps here? Well, the step that a lot of people find the most difficult, those from health sciences, is actually conceptualizing causal pathways. Now, I get a sense from people in the room that this is not nearly as big an issue. Thinking mechanistically about the way in which the world works. But for a lot of health scientists, this is breaking out of big boxes that they've been stuck in for years, because they're taught to think in terms of associations. A is associated with B. And the research questions that they will often bring to a modeling project are about those associations. And it's quite unhelpful from the sake of getting the most bang from those models. They're thinking in terms of the rigid character that they've been taught to think purely for statistical tools, rather than breaking out of it and thinking about things at a mechanistic level or in terms of counterfactual situations. So you might be interested in a research question identifying trade-offs between housing voucher interventions designs in terms of obesity, crime involvement, and graduation rates. How do these different interventions affect different intervention designs for housing vouchers end up affecting these outcomes? And you'll be thinking about mediating factors which might involve physical activity, sedentary behavior, time spent at home, healthiness of diet, that might ripple through to affect these factors. And generally there'll be reciprocal factors, which I haven't shown here. So here's an intervention. It affects these things. It ripples through multiple pathways and ends up affecting some results. Or you're interested in understanding trade-offs between programs to stimulate lifestyle change in terms of their outcomes for childhood obesity and development of type 2 diabetes. So you're interested in understanding how do those affect things like physical activity, social networks, dietary balance, and quantity, and how those end up affecting various outcome measures. And again, there's reciprocal feedbacks I haven't considered here. The point is that in order to build these models, you need to be thinking about the mechanisms, the posited mechanisms. This is not a perfect world, and we're not sure that the mechanisms as we best understand it are accurate depictions. But that's exactly the point about why one of the big reasons we want to model, is so that we can spot when we have an understanding that's not consistent with the evidence, we'll be able to spot that inconsistency sooner. That's something I've emphasized several times. If I want to understand the impacts of shaping interventions for parent-child interactions and how those might affect developmental outcomes, maybe I need a model which depicts some of these factors. Factors having to involve, allostatic load, involving co-regulation and self-regulation on the part of a child, parental regulatory mechanisms, the role of social support, etc. So here we're trying to unpack our understanding of the world into some depiction of causal pathways. And a model is going to need something a lot more specific than this to be able to run scenarios. But by mapping things out, often we can get somewhere that is better than just thinking purely in terms of our heads. So often when we start a modeling project, we work in terms of these sort of diagrams, although more with reciprocal causality such as this one. Now, Jeff and I have, as a long-standing, well, it's not super long-standing, but as an ongoing project the past few years, we have an initiative seeking to leverage this sort of qualitative modeling for agent-based and hybrid models. And the realization here is that model mapping tools such as this have been extremely useful for system dynamics modeling. I don't know how many of you are familiar with causal loop diagrams. So we have variables here, and these variables have clear polarity associated with them, so we could say if it increases or decreases. And we have links between these variables. And a variable A to B that has a link from A to B, then if that link has a plus associated with it, then if A increases, then all other things being equal, B will tend to increase compared to the value it otherwise would have held. If it has a minus sign associated with it, so let's think for a plus, right? If maladaptive behavior becomes higher likelihood, it becomes more common, that tends to increase stressors within the family. So, if a child is acting out, for example, within a family, it tends to set the adults in the family on edge, and they may sometimes snap at the child or what have you. And so it tends to increase the stressors for the child. And so it's a plus there in the sense that if we increase the likelihood of maladaptive behavior, all other things being equal, intensity of stressors will tend to increase compared to the value it otherwise would have had. If there's a minus sign associated with an arrow, let's say from likelihood of maladaptive behavior to social support, if you attempt to increase A, the likelihood of maladaptive behavior, it will tend to decrease B compared to the value it otherwise would have had, all of the things being equal. So it will tend to lower social support. Now, it turns out with a diagram like this, we can reason about, from the links associated with particular variables, we can extend it and reason about links, the polarities associated with whole causal pathways, sort of whole chains of links. And from there, we can reason about the polarity associated with feedbacks. Now, in system dynamics, these feedbacks and the polarities of those feedbacks are of central interest, okay, because the feedbacks are viewed as having really big impact on the system's behaviors. And there's good reasons analytically for understanding that. So diagrams like this, which may seem toyish, actually can be the basis for a lot of insight, in fact, on the modeling level. You can take a diagram like this and get quite a lot out by looking at it. And it turns out building these diagrams is not easy. Building them well is not easy. And with my students, for example, in my classes, if you give a challenge to build up a diagram like this, they'll come up with something that's a start, but there's a lot of refinement that can then be led on it. And with that refinement, you get greater clarity of thinking about what's going on. It's not merely a matter of prettiness, prettifying the diagram. It's a matter of thinking through with clarity what's happening. So these diagrams can be useful. They can also help you, and we have some papers on this if people are interested. They can help you identify key points for intervention, areas, key variables that seem to affect multiple pathways or that are involved in multiple feedbacks. And they can be very useful. So system dynamics world has long used these sort of diagrams for very effective mapping and then reasoning about situations. And there's no reason that we couldn't use a diagram of this form if it's adapted to agent-based and hybrid modeling. Why wouldn't you just want to use this diagram for agent-based modeling? Well, the truth of the matter is I have done that. The problem is it has some shortcomings. There's some limitations in what you can do here. Among other factors, you see factors that are naturally at different levels of scale put down just as different variables into the diagram. Factors involving the policy regime and individual behavior. You'll also see variables involving different people, like child capacity for self-regulation and parental self-regulatory capacity or mechanisms that are sort of just lateral to each other with no distinction about whose they are. They're just sort of horizontal to each other, lateral in this diagram. So in short, a diagram like this ends up compressing down multiple levels of context, multiple different types of agency, all into one diagram. And here's interventions, training efforts. And my thought of it is that when it comes to agent-based modeling, often you end up, because they get compressed in this diagram, you end up trying to separating them out when you're thinking about building an agent-based model from this. You end up, separating those back out and saying, well, this is for the parent, this is for the child, those go in different agents, and this is an intervention that goes elsewhere. So rather than trying to smush it all into one diagram and then deconvolve it later, read it out from there. Jeff and I have been working on a technique that that tries to, from the get-go, adapt these tools to the agent-based and hybrid context. And the idea here is these ideas remain somewhat magmatic, but we actually do have software now that captures some elements of this in a kind of Google Docs-like fashion to allow multiple parties to edit it. And there's a lot of refinement that's still needed there, but we're getting somewhere. We're going somewhere. And we've run, as recently as last week, sessions where we use these kind of mechanisms with stakeholders, with non-modelers, to try to elicit understanding. And so the idea here is that you try to take the best of causal loop diagrams, but you don't stick to them in a rigid fashion. In fact, you start weaving in things like state charts, right? State charts are eminently kind of understandable. You might have stocks and flows. You might have a depiction of agents and flows within agents, and you'll have aspects. Jeff is like the world's genius with these cartoon depictions, but you have levels of context. These are kind of Russian dolls, I think. And then you put people in networks here, and you have groups, and the groups play out, in a geographic context or in a network context, and there's interactions between people. And you can capture factors that might be in the general environment in as much as they influence a person. In many cases, I add in these interventions, which I use lightning diagrams to show where they affect things. So I'll draw an arrow from the lightning diagram to where it affects things, and the lightning diagram would be a particular intervention. So maybe this would be walking school bus, or it will be, early childhood nutrition education, or maybe it will be efforts to promote breastfeeding. And that would end up impacting with arrows. It would show where it goes in the diagram in terms of stocks or flows, or in terms of causal loops, or in terms of state charts. And we might have an event that goes off and shows, okay, some sort of ongoing activity. And then there's some mechanism to represent sort of workflows in the way that we capture through discrete event modeling. So this is kind of a very high-level diagram, but we've worked to try to make it more specific in terms of drawing things out. And much of the goal is to have an agent depicted here with this kind of silhouette, and the things within that agent, the properties of that agent, aspects of their state, aspect of the rules that govern the properties, would leverage these tried and true methods like causal loops, state charts, stocks and flows, and some sort of representative decision making. And those will be placed within that agent. So this might be a child agent, and there'll be a mother agent, or there might be an agent for a clinician, and that clinician might have other aspects of their state or properties of them. And the idea here is that we would use this with stakeholders often for them to kind of to elicit from them some of the factors that they think are most important. So last week we were down in Canberra and used this with members for this task force associated with gestational diabetes, and they ended up putting on dozens and dozens of factors that affected many of these things, and many of them were placed inside the individual. So where they ended up impacting the system. Jeff, do you want to make some utterances on this as well, since you're a co-conspirator in this work?
It's a work in progress. I think I've got a view that policymakers pretty easily understand aggregate level abstractions, but clinicians really want to see individual patients. And so depending on what group you're actually dealing with, you may want to modify your approach. But what we're trying to do is, I see one of the key reasons for doing this hybrid modelling is to bring the policymakers and the clinical people actually looking at where their mental models differ and explicitly representing that difference in the model. And that's really, I guess, the reason we've been, I've been putting up with being on the bleeding edge of some of this software development for about 13 years. There's also a link there's a public link that I unfold this model piece by piece that anyone's interested I can give you. And I'm using a tool called Insight Maker, which is it goes from qualitative mapping to quantitative modelling.
Jeff, could you get me the URL?
Yeah, I could.
Okay. So Insight Maker.
Yeah.
Insightmaker.com.
Yeah, that's fine. Yeah.
Okay. Great.
And if I log in,
here we go. Yeah.
Let's just hit Explore Insights.
Yeah. Jeff is one of the most prolific collaborators.
Concept, I hope.
Concept?
Yeah.
Health?
Concept should do. Yeah.
Okay. So I know this. At first glance. Okay, Jeff, do you want to?
You just scroll down. I'll try and find it.
Wow, thinking like a nurse. That's really interesting. Okay.
Keep going. Yeah. Okay, so this is the latest one. See the conceptual map, sort of the Australian map. Yeah, you've got a Canada
this one,
and we've got next one, the Australian.
Oh, the Australia map.
Yeah, we've moved on. This one I did for a presentation in Adelaide. There's a private version. So the idea here is that we not only build this complex diagram, then we unfold it piece by piece, storytelling. But we can also do simple agent-based and system dynamics models in this thing. It's JavaScript-based, all online, multiple users. It's got some interesting ideas.
Do you want to prop?
Just push it through. I'm no good with buttons.
Okay. Okay. Yeah, and so a lot of the issue here is that different stakeholders have different understanding.
Yes.
And I know these diagrams may seem to you toyish, but if you really see this in practice, ladies and gentlemen, like last week in Canberra, you had multiple people around this diagram that was being built up of the sort that we saw with the silhouette and so on. And there were substantive conversations taking place about how this factor ends up impacting the ones already in the diagram. So it may seem toyish, but actually it brings out a lot of substantive discussion. No, Jeff is a big believer in doing this with kind of more crafty type approaches, right? With elastics and
making it a craft event so people use their hands and learning by doing.
And I must say, I've been very impressed. I had a certain degree of skepticism, but I was very impressed. People crowded around. There were a lot of discussions to people next to them. So the fact that they were, they were
That's it.
sitting next to each other around the diagram was really valuable.
So the idea was we make it into a kind of a war game, and there's a big table with brown paper on it, and then we lay all these things, and people can move stuff around and draw on it. And you can actually shift things and look at making links with tape or blue tack or what. So people are doing stuff and talking about it. It's actually the talking about it
That's the most important.
most important.
Yeah, and often the talking about it will bring out different understanding. I think this impacts this, and someone else will say, no, really it impacts that, probably just through these two other factors. It doesn't impact it directly. And so I'll say, oh, okay, I guess that's right. I'll take away my link, and they'll end up doing theirs. Okay, Jeff, do you want to?
Sorry, Jeff, do you tend to have a professional moderator or, sort of in place in those things?
No, we have unprofessional moderators.
Unprofessional moderators, yeah.
Yeah, definitely.
You know what I mean?
Yeah, we generally find a champion,
Yeah,
and they're usually a trusted person of the group.
okay.
That's the best.
Yeah.
Sometimes you don't have that.
Yeah.
The group that's already got relationship works better, but sometimes you want to throw in a few disruptors just to shake them out of their current thinking. It often depends on what stage of the project you're at or what the purpose is. But no, I don't like content-free moderators. I have React to content-free moderators.
I mean, you want someone who really understands the material.
Yeah.
And there are really content-full discussions that take place. And there's stories often that go along with what's gets put down in the diagram. People have a certain understanding as to why they link this thing to that thing. And one of the things I'm interested in is technology to enable this, but I'll readily say that doing it in person has a lot of benefits. We have this Google Doc-like tool that we had a student group build, which allows you to do it online and simultaneously, but one of the things we want to expand it for is to try to capture the story. So when you add something, you can say something about why you added this, and it can record who added it and at what time, so that you can go back after the fact and see aspects of why this was, why someone thought this was important at that time. Oh, so Jeff, do you want to narrate this story? I think doing it.
People can, but I mean, you can if you see that. If you just go inside, maybe generally it'll. Just play around. You can browse. I can give you the link if you don't want to step through it. But that number 35907 is a good thing to remember if you really want to look at it.
Sorry, the 35.
Oh, see, it's got Insight 35907. So if you just click on anything and then force it in, it will auto-complete the name. All you need is the number to get to the thing.
Right.
And as you say, you pull up on any Insight and then just sort of change the number, it'll work. So again, we're going through this whole thing. The other thing is that there's a lot of, some of the people I work with are sort of heavily into design thinking, and really thinking about what are other methods. There's a whole stuff from Ulrich on critical systems heuristics. A lot of these qualitative mapping, multiple stakeholder views, that I've tried to at least put a few links into some of that stuff.
Are the models that you create more robust if it's based on empirical evidence? The causal pathways, rather than a speculation or rather than anecdotal? Again, I'm thinking like a biostatistician, but
there's very little data on causal pathways.
Sometimes there are, like if it's biologic, there's some data.
Yeah, like if this is shown to lead to that, or if this.
Well, most of them are
behaviour leads to that
associations which are difficult to know what the causation is, whether it's a latent variable. Mostly association in complex systems, the data. Again, you need to postulate a cause and explicitly represent it. Some of it you've got some empirical associations, but they're not causal. The problem is that we want to change that data generating process. So we want to intervene and change what happened. So to do that, we have to postulate a cause and then try to work out whether that cause is plausible and work out what data we need to collect to help reinforce our stuff. So robustness is not about the model, robustness is about the purpose. So a lot of our modelling is robust policy design. So if the model will change our policy, or if the assumptions in a model, if they don't hold, and it means policy A is no longer better than policy B, that's what we want to know. That's not just about a single empirical association. It's about pasting together a whole lot of multiple data sets. Most of them are inconsistent. Almost none of them are time-stamped. So you've assumed some steady state during a 5 or 10 year period. Some assume lifetime steady state. I mean, and again, teasing out all that in terms of an intervention. So it's a very, again, it's a, as James Hansen said, the climate change model. Model is a word for people who can't spell hypothesis. So that's the key to this, I say. And all we're trying to do is how do we get this robust policy design? So that's why I say the model's not robust, but can we have the purpose of the model robust? And so you say, well, okay, would our policy, under what conditions would our policy advice be different? And then we can do some stuff about when that would be. And say, well, listen, we don't really know, but if it's a certain, if this causal factor or interacting with this is greater than that, then that means we'd switch to this different policy. Therefore, we have to go out and measure something we don't know to improve our the robustness of our inference, which is this is what we think this policy is going to work properly, and this is why we think it's going to work properly. But again, a lot of the stuff is convincing people. So to take collective action. So listen, nothing's going to work. My policy is better than your policy unless we can actually convince everybody to take collective action and understand what the trade-offs are and maybe what the compensations are, and also what data we have to collect to make sure the implementation is going the way we think it ought to go. So
this difficulty in health in particular is they talk about evidence-based practice, evidence-based policy, blah, blah, blah. So
there's this much practice and this much evidence. So and the practice is growing much faster than the evidence, so I don't know.
And it's frustrating because unfortunately they're very so blinded by the evidence-based idea that anything that doesn't have evidence they don't even consider. Well, so they're limited in.
Well, what's evident to one person is definitely not evident to another. So that's the big problem. So again, most of this is about how do we resolve these conflicts and understand the nature of them and why they're there. And it's often, as Nate would say, often it's about the language. People are using this, misinterpreting the language of describing a concept. They're using the same words, but they mean different things. So a lot of the model makes it crisp of exactly what you mean, and people say, well, actually, that's not what I mean when I use those same group of concepts. And obviously, that's different for public health, epidemiologists, clinicians, different health professionals. They all have nuances of language.
There's as many cases of unproven healthcare being used as there is this push for evidence-based healthcare.
And I think it's a very good point, because there are areas that are probably extremely important, but the nature of the situation is such as you're not going to be able to readily get evidence about them. Factors involving certain aspects of social and behavioral sort of side of things, where we strongly suspect there's huge leverage points there, but the nature of the situation is you're not going to be able to easily get evidence, and it would be a real shame if it ends up being impoverished, the efforts on those fronts, just because it's the cards are stacked against them. The inability to gather evidence. So I think there's some rich discussions to be had there, and I do want to finish this lecture, but I think you've put your finger onto something. So this would be, sort of a system map where we have, parameters for a person. We have states, we have stocks and flows, we have state charts, we have certain types of interventions affecting certain areas of the state chart. We describe aspects of the environment and so on. Now, a key division that I emphasized early on is between factors that are endogenous to the model for a given model version, exogenous, endogenous things that are produced by the model, generated by the model. The model tells us about them. Exogenous things we tell to the model that are, that indicate pre-specified assumptions, and then things that are ignored or excluded, things that are outside the boundary of a model. So why would you include something? Now, again, this is with respect to a model version, because we're going through successive versions of models as we learn, as we add things in, as our sense of what's important to add in for the stakeholder, add in as an explanatory factor, add in as a causal mechanism. What things are key reasons for adding things in? Well, one reason for adding something in endogenously is if you believe that you can't adequately capture key dynamic behavior over the time frame of interest without some factor, maybe it's some latent factor or it's some particular element of a causal pathway, incorporating that in an endogenous fashion makes sense. If you're interested in diabetes outcomes and you can't reason about that effectively for the time frame of interest without representation of weight, you probably are going to want to have weight in there, or BMI. Food is there? Okay. Another reason is if you want to capture the effect of an intervention, and it ends up affecting this thing that you could put in, you probably, if the intervention to lower obesity depends on weight, it's a good reason to incorporate weight into your model, because you need to represent somehow the effect of this intervention on outcomes. Or if you're intervening on the nutritional environment, you're going to have to reason something about how nutritional environment ends up affecting weight to really adequately capture certain interventions. Yes, Roberto.
When do you start, or where do you start? In the sense that I often have spoken with Jeff and others
Yes.
on these issues.
Yeah.
Whether it's an agent-based, this is an agent-based problem, or this is a discrete event problem, or this is a system dynamics problem.
Yeah.
So they send me to different bushes, and I don't know where to go. So the question is, where do you start? And probably you need to visit the three
you
areas.
throw all that out, that's where you start.
Throw what
You
out?
throw all the methods out, then you start with conceptualizing. Qualitatively conceptualizing.
Yeah, I think if you start to think through what are the issues, some of these things, adding things in here will end up pointing you to certain of the methods as being needed. So if it turns out that social network, let's suppose you're interested, so in the US CDC is listed, has examined various interventions for their efficacy in changing weight. And one of the few that's been highlighted as a type of intervention that can successfully change weight trajectories of people is social support. And if you want to represent at a more articulate level interventions that intervene via social support networks, the effect of daily exercise clubs, to encourage walking on the part of individuals in a rural town or what have you, you're probably going to be thinking about an individual level model, because you need to represent these networks amongst people and pressures from the network to participate, etc. And there that might point you to one sort of modeling, whereas there's going to be other sorts of questions that might intervene at more of a higher level, involving sugar sweetened beverage taxes or what have you, where you might be able to make use of an aggregate model that would characterize the broad impact on the societal weight norms or what have you. in which case it might point you to an aggregate model being a good place to start. So I think the model conceptualization, as Jeff said, ends up driving choice of methods. And you do want to make sure that your research question and the understanding related to it are aligned with whatever research method you use or whatever modeling tool. Okay. Just because I know food is there, I want to complete this slide at least. And I think, as I understand it, we have tighter strictures on food timings today, right?
Yeah.
We can only have defined feeding times.
Well, we're competing.
We're competing with another
We're
group.
competing in the.
Hopefully they won't
feeding
get our
shop.
food.
Exactly.
They have their own, and it's very well labeled.
Yeah.
Okay.
Ours may be superior though.
Okay. So our feeding times are basically 15 minutes instead of half an hour for the teas, and then for lunch it's half an hour window. After which time they're going to eat our lunch. Or?
Not quite that bad.
Okay, that's
maybe the crowding in the lounge is the problem.
okay, ladies and gentlemen. If you're concerned about how something will be affected by an intervention, for example, maybe you're interested in how a given intervention may have transfer effects from one group to another. That low-income people will disproportionately be disadvantaged by this intervention, or lower education people. It may be that those transfer effects will provide a motivation for representing some of that heterogeneity in the model. If you have key observable data that you want to compare with model findings, you may want to, in the model, make sure to represent comparable variables so you can compare it with that empirical data, so that you can compare model results for a given variable with corresponding empirical results. So that would be another reason that you might want it to be endogenously represented, because you need to compare it for building confidence in the model. And finally, if it's very important for stakeholder credibility. Okay, I think we should probably stop for the tea right now, and then we'll reconvene and wrap up this model conceptualization lecture. Yeah, thank you.
Good luck. Yeah.